Hello everyone. Today I will talk about algebraic integers and integrality properties of characters. So let's start with the following three statements for any complex number lambda. So the first statement says that there is a square matrix with all coefficients from Z which has lambda as an eigenvalue. The second one is just a restatement of that, saying that there is a square matrix with integer coefficients whose characteristic polynomial has lambda as a root. Then the third statement says that there is a polynomial, monic polynomial with integral coefficients which has lambda as a root. The equivalence of these three statements are actually quite easy to see. First of all, the equivalence of 1 and 2 does not require any proof because in any first course of linear algebra, it is discussed that an eigenvalue of a matrix if and only if a root of the characteristic polynomial. And to see 3 from 2, basically you just as a we need to have a polynomial which has lambda as a root, so the characteristic polynomial of the matrix A will do the job, and since A has all coefficients in Z, so therefore the characteristic polynomial, which is always a monic polynomial, will have coefficients from Z. Okay, now to prove 2 from 3, what you have to do is you have to consider the companion matrix of this polynomial. So let me remind you what it is. Given any monic polynomial, there is a matrix called companion matrix, which has the minimal polynomial and characteristic polynomial as well as the given polynomial we have started with. So therefore, if we take the characteristic companion matrix of this polynomial, then the characteristic polynomial of that matrix will be this one itself. Hence, lambda being a root of the polynomial, lambda becomes an eigenvalue of the companion matrix. Now, the companion matrix has coefficients 0, 1, and the coefficients of this polynomial. Hence, all the coefficients are from Z. Thus, we are done. Okay, so in view of this equivalence, we will now make a general definition. We say that a complex number lambda is an algebraic integer if that satisfies 1 and in fact equivalently all of the condition of the three statements written above in 1 to 3. Okay, thus by an algebraic integer we will understand it's a root of a square matrix, it's a root of a monic polynomial with integer coefficients, or equivalently the eigenvalue of a square matrix having all coefficients from Z. Okay, so let's look at some definitions. First of all, any integer has to be is all trivial and algebraic integer because if the integer is n, then x minus n is the polynomial. Now, root 2, root 3 in general, nth root of m when m and n are positive integers. These numbers are trivially, these numbers are easily seen to be algebraic integers because you just take the polynomial x to the power n equal to m. Any root of unit is also an algebraic integer because that's a root of such an equation. Thus z to the power minus 1 is the polynomial. Okay, so after just talking about some very common examples, we will now look for the properties of algebraic integers. So the first property that we will see is if lambda is an algebraic integer, then so are lambda minus lambda and conjugate of lambda. This is very easy to see. If A is the matrix whose eigenvalue is lambda and A has all coefficients in Z, then we consider minus A that will also have all coefficients from Z and will have minus lambda as an eigenvalue. Okay, to see lambda bar is an eigenvalue, we will keep the matrix A as it is. Since lambda is an eigenvalue of A, so there is a non-zero vector V. So here V is a tuple, right, in some Cn. So what we will do is we will take the conjugate of each of these coordinates of V that will give me another vector in that Cn, which we denoted by V bar. And if V is an eigenvector of the matrix with respect to the eigenvalue, if V is the eigenvector of the matrix corresponding to the eigenvalue lambda, then this V bar happens to be an eigenvector of the same matrix with respect to the value lambda bar. Okay, fine. Now let's come to 3, which is one of the most important properties of algebraic integers. It just says the sum and product of two algebraic integers are also algebraic integers, and in view of that, one can conclude that the set of all algebraic integers forms a subring of C. Okay, let's look at let's try to prove property 2. So how to prove that? First we'll prove that it's closed under product. So let lambda and mu are algebraic integers, so that means there are matrices like this which has eigenvalues as lambda and mu respectively. So let v and w are the corresponding eigenvectors respectively. Now what we will do is we will regard these matrices as linear maps. So recall that if A is an m by n matrix over a field K, then from A we can regard A as a linear map from Kn to Km, which is given by x, which is x, a vector from Kn is being multiplied by A from the left, and thus it's giving a vector in Km. Okay. So we will regard these matrices as linear maps. A will be regarded as a linear map from Cm to Cm, and B will be regarded as a linear map from Cn to Cn. Then we will take the tensor product of the linear maps. So if we once we take the tensor product, it's easy to see that V tensor W, the image of V tensor W under this map will be a V tensor BW, AV is lambda V, and BW is mu W. So using the bilinearity, we get lambda V times V tensor W. And now just to conclude that it's a eigenvector, one has to just make sure that this guy is non-zero, and that's quite easy, because if you just take the standard basis of Cn and Cm, since V is non-zero, so one of the coefficients of V, when it is written as a linear combinations of standard basis vectors, then one of the coefficients will be non-zero. Same for the tensor product, same for W. So thus when you take the tensor product, then and expand it with respect to the basis EI tensor EJ, then you will see that two non-zero coefficients get multiplied, and yields another non-zero coefficients attached with the basis vector. Thus it turns out to be non-zero. So this linear map has this lambda mu as an eigenvector. Now to finish that, now to finish our proof, we just have to consider the matrix of this linear operator with respect to the standard basis, with respect to the tensor product of standard basis of Cm and Cn. And since we have already discussed that the matrix representation of the tensor product is just basically the tensor product of the corresponding matrix representations. So from that, the matrix representation of this operator will be just the tensor product of the matrices A and B, and hence it has all coefficients in Z. Therefore, this matrix has lambda mu as an eigenvalue, because the operator itself has lambda mu as the eigenvalue. Okay, so that's how we do it for product. The technique for proving that the set of all algebraic integers is closed under addition is exactly same, but we have to be careful. We just can't take A tensor B, because that won't lead us to lambda plus W any by any means. So what we will do is, instead of, we will rather consider this. So IN and IM, they denote the identity operator on Cn and Cm respectively. So now if you consider this tensor product, sum of these tensor products of the linear operators, let me again remind you that we first regard A, B as linear operators and then consider the tensor product. So now it is very easy to see that this applied on V tensor W is this plus this. Hence, from here lambda times V, lambda V tensor W and V tensor mu W. Using bilinearity, we get this. And already we know that this is non-zero. So thus this linear operator has lambda plus mu as an eigenvector. As earlier, now we will take the matrix representation of this operator with respect to the with respect to the tensor product of the standard basis elements. Okay, so thus we get lambda plus mu as an eigenvector of a matrix with integer coefficients. Okay, that shows the set is closed under both addition and multiplication. Now we will prove the property 3, which which actually looks like a quite innocent one, but let me tell you that actually provides us a very powerful and influential technique. In fact, in this lecture, we will see that how influential this is, because the main theorem that we are going to prove, this is the, to prove that this serves as the main technique. And then we will also, towards the end, we will show another example, another application of this technique. So it says that a rational number, if it is an algebraic integer, then it has to be an integer. So that shows any rational number, unless it's an integer, is not allowed to be an algebraic integer. The proof of this is fairly simple. Just we use the definition that since it is a linear, it's an algebraic integer, so there is a polynomial with integer coefficients which has the lambda as a root. Let's write lambda as m prime by n prime, where they are co-prime. Now what you do is, we just since m prime by n prime is a root of this polynomial, so you just substitute it, and that you get 0, and thus you get 0. So therefore now what you do is, we just clear the denominator, so that is multiply everything by n prime to the power n, and then keeping the first term on the left side, we just push the rest to the right hand side. That gives you this. Now this is an integer, therefore this implies n prime divides m prime to the power n. Since m prime and n prime are co-prime, so therefore basically this is possible only when n prime is plus minus 1. That shows lambda has to be an integer. The proof of this is fairly simple, but as I said, that this innocent looking property actually provides us one of the most powerful techniques. Okay, so we will derive two corollaries from these properties. So first of all, basically, so far we have discussed the algebraic integers and their properties. Now I will tell you how and why they are relevant to our context of representation theory. The first corollary shows that it says that if G is a finite group with who's a character of so it says that suppose G is a finite group and chi is a character of G, then for any G, the value of the character at the point G is an algebraic integer. This is very easy to see, because what is chi G? Chi G is the trace of rho G, and since rho G has finite order, so in fact rho G, therefore in fact rho G is diagonalizable, and all its eigenvalues are roots of unity. So chi G is just sum of them, since each root of unity is an algebraic integer, so therefore their sum has to be an algebraic integer. Thus the value of the character is always an algebraic integer. And then furthermore, if the value of the character is rational, So then the value itself has to be integer. Okay, now we will come to the main theorem of this lecture. Uh, it is known as the dimension theorem due to Frobenius. Later on, Schur strengthened it significantly, but for the time being, we will deliberately skip the Schur's contribution. Rather, we will stick to the proof of the original theorem by Frobenius. So this is the statement of the theorem that for a finite group, the dimension of any reducible representation uh, has to be a divisor of the order of the group. Well, here I have written degree, which is nothing but by definition dimension. Some author prefer to call it a degree instead of dimension. So, but I mean, here we'll just stick to the terminology dimension. Okay, so they are the same. It is just up to the choice of people. Okay. Okay, so in order to prove that, we will first make two observations. Okay, so here there is a slight problem. So uh, uh, whatever I have written uh, whatever I have written in this first point, there is a serious mistake which I realized later on. So I will suggest you to ignore that completely and instead look at look at what I am showing you now. So ignore what is written in 1, rather you should see this. So this is what we have already discussed, that suppose G is a finite group and B is an irreducible complex representation of a G, and then if F is a class function defined over G, then we define rho F like this, which we have verified to be a G invariant linear map from V to V. Now using Schur's lemma, we can say rho F has to be the scalar multiple of identity, and the scalar can be computed like this. So this we have seen already in the class. Now we will just consider a special case of that. So in the very special case when F is the characteristic function of the conjugacy class of a group element X, so that is, you just take a group element X, consider it conjugacy class, and they can take the characteristic function of that class, which just takes the value I want identically on the on Cx and 0 elsewhere. Then for that the value of lambda turns out to be this. Okay, because when F is the characteristic function of the conjugacy class, so basically this will be chi x times the order of the conjugacy class, which is trivially this by Orbi stabilizer theorem, and divided it by order of G. So then order of G gets cancelled. So this is how this is what we get after that. Okay, so keeping this in mind, keep this in mind. So now let's get back to this. Let's get so yeah, as I said that you just ignore what is written in point on, rather keep in mind what I have just shown you. Now let's we'll just discuss the second point. So the second point says if G is a function, if F is a function defined over G, which always takes integer values, then for such a function, once we consider this linear operator on LG, so it has to be linear operator, right? Because each RG is a linear operator on LG, and we're just taking a linear combination of them. So now we will show that any eigenvalue of this operator is an algebraic integer. The proof of this is also quite immediate. recall that we have a basis of Lg, namely this one, with respect to which the matrix of Rg turns out to be a permutation matrix. So hence it has all coefficients in Z. Therefore, this operator has a matrix representation which has all coefficients in Z. So any eigenvalue of this operator will be automatically an eigenvalue of the matrix representation of this, and since that has all coefficients in Z, so therefore the eigenvalue has to be an algebraic integer. Okay. Okay, that's good enough. Now we will so the we will consider a special case of this. So if so, again, just let me remind you that this is for any function that takes values in Z. Now, in particular, if we take f to be the characteristic function of the conjugacy class, then this operator is actually, this operator turns out to be this. Okay. Now we restrict this operator on any reducible subspace of subspace of subspace W of Lg. Okay. So since this is irreducible, so this operator on W has to be a scalar multiple of identity, and the scalar has to be this, because that's what we have just computed here for any reducible representation. Now here V is just W, which is a irreducible subspace of Lg. So the scalar is this. So this operator on W becomes a scalar multiple of identity. The scalar is precisely this, where chi is the character of the subrepresentation of R on W. And since this is on W, it is just a scalar multiple, so the scalar has to be automatically an eigenvalue. So thus, from as a consequence of what we have just discussed here, we arrive at the conclusion that this has to be an algebraic integer, and since every reducible representation of the group G is always contained in the left regular representation R, so from that we conclude that this is always an algebraic integer for any character chi of G. Okay, because we know that given any character, there is a subrepresentation of the left regular representations which has chi as the character. Okay, because of we know that isomorphic representations have the same character. All right, so we got that this is always an algebraic integer. Now from here it follows that this times chi g bar is also an algebraic integer, because chi since chi g is an algebraic integer, conjugate of chi g is always an algebraic integer, and this is an algebraic integer, chi g is an algebraic integer, so is their product. Okay, so based on this observation, we will come to the proof of our dimension theorem. So what we will do is we'll first label the conjugacy classes of the group G. Let's label them as C1 to Ck. So these are all distinct conjugacy classes. We then take a representative from each of these classes. Let's label them as GIs. Okay. So now, since chi is in reducible character, from the orthogonality relation, inner product of chi with itself will be 1. And then we just write what this inner product is. It is just 1 by order of G times this. Now you see that, so this sum is over all group elements G. So we'll break this sum into k parts, and so we'll break this sum into k parts as follows, that on each part I will take the sum on a conjugacy class. So let me show you what I actually mean. So uh, so we have this sum G in G. Okay, so we will break this sum in the following way: G in C1, G in C2. Break the sum into K parts. Okay, and the reason for doing this is the following. So suppose when you consider a typical sum of them, G in Ci, chi G prime, then you see that since characters are always class functions, so all these summands are same, and therefore since we have chosen Gi as the representative of Ci, so this is basically chi Gi times chi Gi bar times the number of elements in the conjugacy class, which is precisely order of Cgi, right? So that's what happens to each and every summand. So keeping this in mind, once we come back, we see that this sum actually happens to be this sum. This sum turns out to be this. Okay. Now from here it's immediate that order of G divided by dimension of the character chi is just this sum. Okay, now we know that each of the summands is algebraic integers, so is their sum. So therefore this is a rational number which happens to be an algebraic integer. Hence, in view of the third property, it turns out to be an algebraic, it turns out to be an integer. So again, let me tell you the main trick or technique of the sectorial technique behind this proof. We're supposed to show that chi1 divides mod order of G. In other words, mod G by chi1 is an integer, but above, so there is no direct way of showing that. We just know a priori it's a rational number. So then what we will do is, since we know it's a rational number, we since we know it's a rational number, so we will show that it's an algebraic integer. Therefore, from that it will automatically be an integer. Okay, so let me let me just finish here. I will just as I have told you that the main technique, which one of the most powerful techniques will be the following one. When we want to show that something is an integer, we first show it's an algebraic integer, and if beforehand we know that that's a rational number, then using property 3 it will turn out it will be an integer automatically. Okay, so in the next video we'll show some applications of them, and some applications of this dimension property. Okay, so let's stop here.